Okay, so our first topic is parametric curves. Okay, and these are sort of different from our usual style of thinking about calculus. So in first year calculus, we work with curves in the following format. Okay, we have some function. Right? We input values of x. And our function does some kind of magic and outputs a value of y for us. Okay, so we have input output y. Okay, that's our sort of our usual way of thinking about functions. Okay, now we're going to sort of generalize this to a sort of a new way of thinking about functions, one where we have multiple outputs. Right? So here we have one input, one output. In parametric curves, we have multiple outputs. Okay, so in a parametric curve, we start with the same axes, but now we output pairs of points. Okay, so we get a point that has two outputs, and this is why we have several variables. Most of the examples in this course will be two variables. So here we're going to have one input t, okay, so here will be our several variable outputs. So let's plot a specific example of a parametric curve. Okay. So here we're assigning both x and y at the same time. We have a particular value of t, and then we plot where that point winds up. Okay. So in order to plot these things, we're going to go all the way back to sort of grade 9. We're going to make a table of values. So we'll take some values of our parameter and then plot where they wind up. Okay, so if I look at several different values of t, for each of those values, I can calculate what my x coordinates should be. It should be the same as t. And then my y value, I'll get by squaring the value of t. Okay, so now we can put those dots, those points on the plane and see what we get. Okay, so at -2, we get that x is -2, y is 4. All right, so there's our plot corresponding to this point. Okay. Now we'll go to -1. Okay, so for each value of t, we're getting some point on this curve, right? So this would be the value t is -2, t is -1, t is 0, t is 1, t is 2. Okay, so our point is moving along as we change the values of t. And it traces out a curve something like this. Okay? So we can imagine this as sort of a direction of travel, as a path that we go in the plane. Okay. Are there questions there or thoughts there so far? Yes?
Why don't we plot them in R cubed?
Aha, right. That's a sweet question. So when we think about functions like this, so here we've got a function that goes from r into r squared, right? So the outputs of this function should live somewhere in plane, right? They should live in this R2 here. Yeah, nice. We're eventually, in like a couple weeks, we're going to plot things in space. But today we'll just focus on the plane. Okay, are there other questions there? Yes?
Is it really a function?
Is it really a function? Yes. So for every t value, we're going to get a unique output. Oh, sorry. For every t value, we're going to get a single output, right? So it's not like t will split into two values.
If you treat that circle as a function, that will fill the vertical tensor.
Yes, yes, that's a very important point. So in our first year class, we had this notion of the vertical line test for being a function, right? Every vertical line has to meet our graph in one spot. Right? If a graph is a function, every vertical line meets the graph at most once. Right? Every vertical line will hit it in at most one spot. And that's because we are functions of x. Right? So for every x value, we need a unique output. Right? We need to be able to get a number, do some calculation, and get an output. Here, right, the curves that we obtain in a parametric equation might not be functions of x. picture we obtain might not be a function of the variable x. Yes?
Does that mean if we want to do something like the vertical line test for a parametric equation, as long as it doesn't go over itself, like it loops, like you have a point and then it loops over the point again, because that means that you have two values of t that would have the same x and y.
Right. So that would mean that the function's not, that means that for every t value, you have some outputs, but you might have two inputs that go to the same spot.
Yeah.
But that's okay, right? That would be sort of like, for this guy, we've got two inputs that go to the same spot.
Oh, okay.
I'll write down a parametric thing which is not a function of t for you, just to give you a sense of what we're talking about, okay? Okay. Sometimes in math it's useful to have non-examples, examples of things that don't quite work. Okay, so this is not a parametric curve because it is not a function of t. So here, if I input t equals 1, then t equals 1 will give me two outputs that kind of split. Yes?
So basically, the function isn't one-to-one.
Yes. Yes. So yes. So you could, yes. The function's not one-to-one. Yeah.
So then we could do the vertical line test if we do it on R cubed and then pass the line through the t-axis.
We will get there. Not today, but we will get there. Yeah.
Okay.
Yeah. We'll talk about these issues in R3 in a couple weeks. Okay. So that's some examples of parametric curves. So here's something where we don't have a unique output. Right? We want to be a function, so for every input we need a single output. Yes?
Are x, y the outputs or x, y the inputs?
X, Y are the outputs. So T is the input. And then, wait, yeah. Yeah. So if you're sort of thinking in computer programming terms, a parametric curve is something with two outputs, or something that outputs arrays of size 2. Okay. Very good. So I want to finish off with sort of one major example that we'll keep coming back to in the worksheet. Here's sort of my favorite example of a parametric curve. 90% of the stuff that we're going to talk about we can check with this example. Right. So how do we plot things? We make a table. Oh, sorry. Yes.
Wouldn't we have to see where cosine, sine exist so that they exist everywhere?
Right. They exist everywhere. Yeah. So this is going to be defined. For all times t, right? Oh yes, that's sort of an interesting interpretation. Some people interpret the variable t as being a measure of time. So you imagine yourself walking along at time t, you wind up at this position. Okay, it's a helpful physical way to think about what a parametric curve does. Okay, so to plot this, we'll make another table of values. Should point something out. When I put these little hashtags, that's signaling that the thing I'm writing down is a comment about the solution. If you hand it in, or if you got a quiz or in a test environment, you didn't write the hashtags, that'd be fine, you'd still get full marks, but I'm saying that this is not part of the solution, it's describing the steps of the solution. Okay? Helps people organize their notes, I find. Okay, so here we're dealing with the trig functions. The trig functions are usually easiest to understand at multiples of pi. So we'll go pi by 4, pi by 2, pi, and I guess we might as well include 0. Okay, so when we plug in 0, cos will give us 1, sine will give us 0. Yep. What do we get when we plug in pi by 4? What happens at pi by 4?
1 over root 2 and 1 over root 2.
Yeah, I heard several 1 over root 2s. Good. Good, good, good. And if